Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are diving deep into the fascinating world of hashing algorithms, which are one of the most fundamental concepts in computer science and cybersecurity. Whether you are building secure applications, managing databases, or implementing blockchain technology, understanding hashing is absolutely essential. Think of a hash function as a digital fingerprint generator. Just like every person has unique fingerprints, every piece of data can generate a unique hash value. But here is what makes it special. While you can easily generate a fingerprint from a person, you cannot recreate a person from their fingerprint. That is the beauty of hashing. In this presentation, I'll take you through everything from basic concepts to advanced implementations. We'll explore real-world applications, compare different algorithms, and I'll share some practical examples from my experience implementing these in production systems. What is hashing? Let me explain hashing in the simplest terms possible. A hash function is a mathematical algorithm that takes an input of any size, whether it's a single character, a massive file, or anything in between, and produces a fixed size output called a hash value or digest. The magic lies in three key properties. First, it is deterministic. The same input will always produce the same hash. If you hash the word hello a million times, you will get the same result every time. Second, it is one-way. You cannot reverse engineer the original data from the hash. And third, it has what we call the avalanche effect. Change even a single bit in the input, and the output changes dramatically. I remember when I first encountered hashing while building a user authentication system. I was storing passwords in plain text. Rookie mistake, until a senior developer showed me how hashing could protect user data even if our database was compromised. That was my aha moment, realizing that we could verify passwords without ever storing them. The diagram on the slide shows this transformation process. Notice how data of any size gets compressed into a fixed size output. This is crucial for many applications, from creating digital signatures to building efficient data structures. Key properties of hash functions. Now let's dive deeper into what makes a good hash function. These properties aren't just theoretical concepts, they're the foundation of secure systems worldwide. Deterministic behavior is the bedrock. When I hash a file to verify its integrity, I need to know that the hash will be identical every time. This property enables everything from password verification to blockchain mining. The one-way property, also called pre-image resistance, is what makes hashing secure. Even with unlimited computing power, you shouldn't be able to work backwards from a hash to find the original input. This is why we can safely store password hashes in databases. The avalanche effect is fascinating. Change hello to hello. Just one bit difference, and the SHA-256 hash changes completely. This sensitivity ensures that similar inputs do not produce similar hashes, preventing pattern analysis. Fixed size output is incredibly practical. Whether you are hashing a 1 KB file or a 1 GB video, SHA-256 always produces a 256-bit hash. This predictability is essential for database design and network protocols. Finally, collision resistance means it should be computationally infeasible to find two different inputs that produce the same hash. While perfect collision resistance is theoretically impossible, due to the pigeonhole principle, good hash functions make collisions so rare they are practically non-existent. Popular hashing algorithms. Let me walk you through the most important hashing algorithms you will encounter in the real world. Each has its own strengths, weaknesses, and ideal use cases. MD5, despite being cryptographically broken, is still widely used for non-security purposes. I still use it for quick file integrity checks during development. It's fast and produces a 128-bit hash, but never use it for security-critical applications. SHA-1 was the standard for years, producing 160-bit hashes. However, Google demonstrated a collision attack in 2017, effectively retiring it from security use. You will still see it in legacy systems and Git commits, though Git is moving away from it. SHA-256, part of the SHA-2 family, is currently the gold standard. It is what Bitcoin uses for mining, what many certificate authorities use for digital signatures, and what I recommend for most security applications. The 256-bit output provides excellent security margins. SHA-3, the latest edition, uses a completely different internal structure called the sponge construction. While not necessarily better than SHA-2, it provides an alternative if SHA-2 ever becomes compromised. Bcrypt is special. It is specifically designed for password hashing. Unlike the others, it is intentionally slow and includes a salt automatically. The work factor can be increased over time as computers get faster, maintaining security against brute force attacks. How hashing works. Step by step. Let me break down exactly what happens when you hash data. Understanding this process helps you appreciate why hashing is both powerful and secure. First, your input data gets converted to binary format. Text, images, or any digital content ultimately becomes a series of ones and zeros. For example, hello in ASCII becomes specific binary patterns. Next comes padding. Most hash algorithms process data in fixed-size blocks. For example, SHA-256 uses 5 12-bit blocks. If your data does not fit perfectly, padding is added following specific rules. This includes appending a 1-bit, then zeros, and finally the original message length. The initialization phase sets up internal variables. SHA-256 uses 8 32-bit words initialized to specific constants. These constants are the fractional parts of square roots of prime numbers, which is pretty clever. The compression function is where the magic happens. Data blocks are processed through multiple rounds of mathematical operations, including rotations, XORs, additions, and nonlinear functions. SHA-256 performs 64 rounds of operations per block. Finally, all the processed values are combined to produce the final hash. The beauty is that this process is very fast, but practically impossible to reverse, thanks to the one-way mathematical operations involved. When I implement hashing in applications, I rarely manually code these steps, as libraries handle it. But understanding the process helps you choose the right algorithm and troubleshoot issues. Real-world applications. Hashing isn't just theoretical, it's everywhere in modern technology. Let me share some real-world applications I've worked with and seen in production systems. Password storage is probably the most common use case. When you create an account on any decent website, your password is hashed before it is stored. When you log in, the password you entered is hashed and compared to the stored hash. Even if hackers steal the database, they can't retrieve your actual password. Data integrity verification is crucial for downloads and file transfers. Have you ever noticed those MD5 or SHA-256 checksums next to download links? They let you verify that the file has not been corrupted or tampered with during transfer. I always verify checksums for critical software downloads. Digital signatures combine hashing with public key cryptography. When you digitally sign a document, you are actually signing a hash of the document. This is much more efficient than signing the entire document and provides the same security guarantees. Blockchain technology fundamentally relies on hashing. Each block contains the hash of the previous block, creating an immutable chain. Bitcoin mining is essentially a race to find a specific hash pattern. The Merkle tree structure shown uses hashes to efficiently verify transactions. Hash tables, one of the most important data structures in computer science, use hash functions to achieve O of 1 average case lookup time. Every time you use a dictionary in Python or a hash map in Java, you are benefiting from hashing. Security considerations. When it comes to security, not all hash functions are created equal. Let me share some critical considerations from my experience securing applications. Collision attacks are when attackers find two different inputs producing the same hash. MD5 fell to collision attacks in 2004, and SHA-1 followed in 2017. The birthday paradox means collisions are more likely than you would intuitively expect. For a 128-bit hash, you would expect a collision after about 2 to the power of 64 attempts, not 2 to the power of 128. Rainbow tables are pre-computed hash lookups that can crack simple password hashes in seconds. I have seen entire databases compromised because passwords were hashed without salts. A salt is random data added to each password before hashing, ensuring identical passwords produce different hashes. Length extension attacks affect certain hash functions like MD5 and SHA-1. Attackers can append data to a message and calculate a valid hash without knowing the original content. This is why HMAC, or hash-based message authentication code, exists. It is specifically designed to prevent these attacks. When hashing passwords, never directly use fast cryptographic hashes like SHA-256. Instead, use specialized password hashing functions, such as bcrypt, scrypt, or argon2. These functions are intentionally slow and memory-intensive, which makes brute force attacks impractical. I typically use bcrypt with a work factor of 12 or higher. The code example shows proper password hashing with bcrypt. Notice how the salt is handled automatically, and you can adjust the work factor for security/performance balance. Performance comparison. Performance matters when you are hashing millions of files or handling thousands of authentication requests per second. Let me break down what I have observed in production environments. MD5 is blazingly fast. On modern hardware, you can hash gigabytes per second. This makes it excellent for non-security purposes, like deduplication or cache keys. I still use MD5 for ETL pipeline integrity checks where security is not a concern. SHA-1 is about 30% slower than MD5 but still very fast. Despite being deprecated for security use, its performance makes it suitable for non-cryptographic applications where you need more bits than MD5 provides. SHA-256 is roughly half the speed of SHA-1. But we are still talking about hundreds of megabytes per second on a single core. For most applications, this is more than adequate. The security benefits far outweigh the performance cost. SHA-3 is generally slower than SHA-2 on current hardware. However, specialized implementations can be competitive. Its different internal structure, known as a sponge construction, offers interesting trade-offs and flexibility. Bcrypt is intentionally slow. That is a feature, not a bug. On the chart, you will see it processes only kilobytes per second, not gigabytes per second. This slowness prevents brute force attacks. I typically aim for 100 to 200 milliseconds per hash for user passwords. This is slow enough to frustrate attackers but fast enough for legitimate users. Remember, for password hashing, slower is more secure. For data integrity or hash tables, faster is better. Choose your algorithm based on your use case. Implementation examples. Let's get practical with some real code examples. I will show you how to implement hashing in different programming languages for various use cases. The Python example demonstrates 3 common scenarios. First, we hash a simple string using SHA-256. Python's HashLab makes this straightforward. You create a hash object, update it with your data, encode it to bytes, and then retrieve the hexadecimal digest. The second example demonstrates file hashing with chunked reading, which is essential for large files that do not fit in memory. I have used this pattern to verify multi-gigabyte backup files. The third example uses bcrypt for password hashing, and shows how to hash a password and verify it later. The JavaScript example uses the WebCrypto API, which provides cryptographic functions in browsers. This is perfect for client-side hashing. However, Remember that client-side password hashing does not replace server-side hashing. Instead, it is a defense-in-depth strategy. The async/await pattern is necessary because crypto operations can be computationally intensive. Notice how each language has idiomatic ways to handle hashing. Python uses a builder pattern. JavaScript uses promises, and most compiled languages offer both high-level and low-level APIs. The key is understanding your language's standard approach and following established patterns. In production, always use well-tested libraries rather than implementing hash algorithms yourself. The examples shown use standard libraries that have been vetted by security professionals. Best practices and future of hashing. After years of working with hashing in production systems, I've learned some valuable lessons. Let me share the best practices that will save you from security headaches. First, assume that hash functions will eventually be broken. MD5 was considered secure for years, as was SHA-1. Plan for algorithm agility. Design your system so you can upgrade hash functions without breaking everything. Store the algorithm version with your hashes. For passwords, always use a proper password hashing function with Salt. I can't stress this enough. I've seen too many breaches from unsalted or fast-hashed passwords. Use bcrypt, Script, or Argon 2, and increase the work factor as hardware improves. For data integrity, consider your threat model. MD5 might be fine for detecting accidental corruption, but use SHA-256 or better if you're worried about malicious tampering. Always verify hashes from trusted sources. Looking to the future, quantum computing poses interesting challenges. Current hash functions are considered quantum resistant, unlike many encryption algorithms, but research continues. SHA-3 provides a different construction that might prove valuable if SHA-2 weaknesses emerge. Post-quantum cryptography is actively developing new hash functions with even stronger security guarantees. While not needed today, staying informed about developments helps you make better long-term architectural decisions. Remember, hashing is a tool. Like any tool, its effectiveness depends on using it correctly for the right purpose. Stay updated with security advisories, follow established patterns, and always consider your specific security requirements. Thank you for your attendance. Please consider subscribing to the channel.